What are p-values and how to interpret them? In this video, I'll define what a p-value is. Then I'm going to describe and criticize the threshold or alpha cutoff approach to interpreting p-values. And finally, I'll describe and advocate for the continuous p-value approach to interpreting p-values. When you compute a test statistic, for example, a t-test, you get an obtained t-value and that t-value's p-value, which is the probability that that t, or more extreme t's, would occur if the null hypothesis is true. For example, if you had a data set of 103 people and you analyzed that data, and you got an obtained t-value of 1.9, its p-value would be p equals 0.06, two-tailed. Now, what does that two-tailed 0.06 p-value actually mean? The figure on the right of your screen will help you visualize what this p-value actually means. The obtained t-value of 1.9 is located on the positive side and the negative side because this is a two-tailed t. If the null hypothesis is true, these t-values, the t-values to the left of the left arrow and to the right of the right arrow, would occur 6% of the time due to sampling error. In other words, the p-value is an index of how likely the outcome would be to occur due to sampling error, assuming the null hypothesis is true. Smaller p-values, smaller areas in the curves, would reflect a smaller likelihood that a given result could result from sampling error if the null hypothesis is true. It's important to understand that p-values can range from 0 to 1. There's two outcomes on your screen. The first outcome, again based on a sample size of 103 people, had a t of 1.9 and a p of 0.06. And you can see that it has a relatively small p-value. Outcome 2, based on the same sample size, had a t of 0.4 and it has a relatively large p-value, 0.69. That's reflected in the shaded areas of the two respective curves. The second outcome has a much higher p-value, and so its outcome is more likely to have occurred due to sampling error. The first outcome has a smaller p-value, and smaller p-values are stronger evidence against the null hypothesis. And again, the null hypothesis is essentially the notion that sampling error created any difference that exists in the data. Now that we've described what a p-value is, we can now talk about some of the ways that p-values have been interpreted. One of the most traditional ways to interpret p-values is the threshold or alpha cutoff approach. In this approach, you select an alpha value ahead of time. Then, after you compute your p-value, you compare your p-value to the alpha value. Typically, the alpha value would be something like 0.05. If the obtained p-value was less than or equal to 0.05, the result is deemed to be significant, and you would conclude that there is sufficient evidence to reject the null hypothesis. Again, that would mean that you are saying the result probably didn't occur due to sampling error. If, however, the p-value was greater than 0.05, the result is said to be not significant, and there is not sufficient evidence to reject the null. This traditional approach to interpreting p-values has its problems, not the least of which is that similar results can lead to opposite conclusions. For example, in outcome 1, you have an obtained t-value of 1.9 and a p-value of 0.06. Using the traditional cutoff approach, this is not sufficient evidence to reject the null. However, in outcome 2, you have a very similar t-value and a very similar p-value, but in this case, the evidence is sufficient to reject the null. Two very similar results led to opposite outcomes. That's problematic. Another problem with the threshold approach is that in some circumstances, different results can lead to similar conclusions. For example, in outcome 1, you have a p-value of 0.06. In outcome 2, you have a p-value of 0.69. Clearly, based on what we learned about p-values earlier, the 0.06 is much stronger evidence against the null hypothesis than the 0.69. But in both of these situations, you would describe the outcome as not significant and you would not reject the null. This is really neglecting to take advantage of the differences between these two p-values. Again, the p-value of 0.06 is clearly suggesting that there might be something in the data that's worth exploring further. However, a p-value of 0.69, assuming there's no other problems with the data, kind of suggests that maybe you need to look for another hypothesis. It'd be nice if you could take advantage of the information that's provided to you in these different p-values. The same problem occurs when you consider two results that were both significant. In outcome 1, the p-value is 0.05, again suggesting you reject the null. In outcome 2, the p-value is 0.003, much smaller. You would also reject the null here. However, both of these p-values are not similar in terms of the strength of the evidence they provide against the null. Outcome 2 provides much stronger evidence against the null than does outcome 1. Now that we've identified some of the problems with the threshold or cutoff approach to interpreting p-values, let's consider another option. As we learned, p-values can vary along a continuous scale from 0 to 1. So rather than dichotomizing a p-value and categorizing a p-value as significant or non-significant, let's actually interpret the p-value as it is. Lower p-values are stronger evidence against the null hypothesis. So one way we can describe these p-values is by developing a language that reflects the change in strength as a p-value is getting smaller. If you look at the guidelines for interpretation in this chart, you can see that one way of thinking about a p-value is p-values are, if they're close to 0.2 or higher, that data might be seen as being consistent with the null hypothesis. However, as p-values get smaller, you can see that their strength of the evidence gradually gets stronger. So p-values close to 0.1 might be considered as weak evidence against the null. P-values close to 0.05 might be considered as moderate evidence against the null, and p-values of 0.01 would be considered strong evidence against the null. Now let's return to some of the previous examples to see if this new approach gives us an advantage over the threshold approach. In outcome 1, we have a p-value of 0.06, and we would conclude that that is moderate evidence against the null. In outcome 2, we have a p-value of 0.05, and we would again conclude that this is moderate evidence against the null. Similar results led to similar conclusions. In this next example, outcome 1 has a p-value of 0.06, and we would conclude that that is moderate evidence against the null hypothesis. Outcome 2 has a p-value of 0.69, and this data would be judged to be consistent with the null hypothesis. Here, different results led to different conclusions. The continuous p-value approach also has advantages when considering two significant outcomes. In outcome 1, you have a p-value of 0.05. Again, moderate evidence against the null. In outcome 2, you have a p-value of 0.003, which would be considered very strong evidence against the null hypothesis. While both of these things would meet the criteria for a significant result in terms of the threshold approach, Using the continuous p-value approach allows you to gain more information from the actual data, a more precise, more accurate characterization of the strength of the evidence against the null hypothesis. But how would this continuous p-value approach have you deal with p-values that fall in between these interpretation guidelines? For example, in outcome 1, the p-value is 0.027, which falls right between 0.01 and 0.05. And outcome 2, there's a p-value of 0.08 between the guidelines of 0.05 and 0.1. Simply combine the labels. A p-value of 0.027 is moderate to strong evidence, and a p-value of 0.08 is weak to moderate evidence. Again, what we're trying to accomplish here is a language that captures the gradation of the p-value. As the p-value gets smaller, the evidence gets stronger, and our language should reflect that. The continuous p-value approach does represent p-values better than the dichotomous threshold approach. However, it does have some limitations. You need to recognize that you cannot compare p-values across studies. P-values are very specific to the study that generated them. They're influenced by sample size as well as other factors. Therefore, you cannot compare p-values across studies fairly. If you're interested in comparing results across different studies, you need to use an effect size. We have a video that describes what effect sizes are and how to interpret them accurately. The concluding point here is that within a given study, interpret smaller p-values as stronger evidence against the null hypothesis. If you're interested in reading more about how to interpret p-values, here are a list of readings to get you started. If you're interested in learning more about statistics, visit us at learnstats.com.